Hey everyone. This is the summary of the R Help session from 28th of September 2018. Today I'm going to be talking about multiple linear regression. The first thing that we're going to be talking about is interpretation of the summary statement of a multiple linear regression. The second thing is the assumption checking, the linearity, independence, normality, and equal variance assumptions. And the third thing we'll be talking about is multicollinearity and the use of the VIF function. The help sessions RMD file has been uploaded onto your Canvas page and can be found if you go to your Canvas page to the course page. Files are markdown. It should be available as the RHED session from the 28th of September. Now, the dataset that we're going to be using for the multiple linear regression analysis is a houses dataset that can also be found in your course's Canvas page. All you need to do is go to datasets and check out houses.csv. So let me read in this data file. All you need to do is download that data file and save it in a folder where you're conducting to the course folder that you've created for STA 371. So I'm running this line now, and I want to view the data set now. So view houses. You can see that this data set has a lot more variables. So what we're doing here is we're predicting price of a house based on a lot of other variables like lot size, waterfront, age of the house, land value upon which it's built, whether it's new construction or not, central air conditioning, if it's present or not, and many other variables like the number of bedrooms, fireplaces, bathrooms, total number of rooms, and stuff like that. So we're going to be running a multiple linear regression um, that predicts price from living space, land value, and whether the house has a central air conditioning system. So I'm creating the model and I'm naming it as model underscore house. It is an LM statement, a linear model statement of Y, which is my price, against three x's, which would be living area, land value, and central air. And after that, I'm referencing the data from which I'm using the model. So if I run this statement, it should run, and I'm getting the summary of the model. As you can see from your screen, the summary of a multiple linear regression analysis is quite similar to the summary from a simple linear regression, with just two extra coefficients added to the summary. So in my case, the intercept term would be that term, would be that estimate. So the estimate of that intercept would be the value that y assumes when all of my x variables go to 0. So when living area is 0, land value is 0, and central RKS equals 0, then the house would be priced at $2,075, which does not really make sense, but that's what the model has calculated. Well, um, and apart from that, you see the three x variables that we've input into the model, and you can see that it's shown estimates and standard errors associated with those estimates for all three x variables. So how do you interpret the estimate or the coefficient of each of your x variables in a multiple linear regression as compared to a simple linear regression? The main difference is that in multiple linear regression, the estimate of any of your x variables is that amount by which y varies for 1 unit increase in that particular x, holding all the other x's constant. So if I hold land value constant and central air, yes, equals it to constants, then the living area, if it increases by 1 unit, the rent should increase by 8.67 times 10 power 1, which is $86.71. So that is how you interpret the estimates of a multiple linear regression. And as you know by now, R does not print the exact estimate, so there is always a standard error that's associated with the estimates, which can be used to calculate the confidence intervals for each of your estimates that I'll be doing pretty soon later. So now that we talked about the estimates and the standard errors associated with the estimates, I'll go ahead to the t-values and the p-value. You can see that there are significance codes printed next to your p-value. All you need to do is go here and see what those significance levels are. If you see 3 stars near your p-value, it means that it's significant at 0.1% level and above. So if you say that your variable is significant at a 0.1% significant level, it would obviously be significant at a 5% or a 10% level as well. 2 stars show that it's significant at a 1% level. 1 star shows that it's significant at a 5% level. A dot shows that it's significant at a 10% level. And nothing shows that it's not significant at all. So as you can see from the output, all the 3 x variables are significant at the 0.1% level, which means they are obviously significant at the 5% level as well. So I can say that this is a reasonably good model because all the variables that we've chosen for the model are significant. And this can also be looked at using the p or the t values. You need to know that the t value should be high, or the fact that the p value should be a number less than 0.05. So if for a significance level of 5%, the p-value should be less than 0.05, which means that any value below 0.05, you would reject the null hypothesis that h naught rather beta, the slope associated with that variable equal to 0 would be the h naught. That is, the x variable does not significantly explain the y. So you're rejecting that null hypothesis and accepting the alternate hypothesis that the x variable significantly explains y. And that's how you interpret p-values. Apart from that, it shows you residual standard error. It shows here that the residual standard error is 61430 on 1724 degrees of freedom. The degrees of freedom here represents the number of samples that you take. This data set I think it has a lot of samples. Let me check quickly how many that would be. I think, yeah, it's close to 1728. So it's calculating 1724 degrees of freedom, accounting for the residual standard error. And the multiple R-squared value for the model is 61%, and the adjusted R-squared value is 61% as well. Apart from that, you have the F statistic and the overall p-value for the model, which tells you that the model is significant again. Now, as we did with simple linear regression, we can use the predict.lm statement to find the mean home price by entering values for each of the predictors. So suppose I want to know what the price of a house that has a living area of 1,400 square feet, a land value of $27,000, and has a central air conditioning unit. I can use the predict.lm statement. Because I've already built the linear model and named it as model_house, I call that model and I type in a comma. So how the predict.lm statement works is these are the parameters that are associated with the predict.lm statement. So first you can see that you have to specify the object. The object in my case would be model_house. And then you have to specify the new data, that is the set of x variables that you want to find your y value for. So in my case, since I have more than one x variable, I have 3 x variables, I have to put them in the form of a list. So list of all the 3 x variables that I want and the values associated with them. comma, and now I have to specify whether I want a prediction interval or a confidence interval. And by doing that, I've specified that I want a prediction interval. So this should give me a fit value of the price, which would be the price of the house, and then a lower prediction interval and an upper prediction interval for that same value. And mind you that if you do not enter what the level is, it always assumes that it's a 95% confident level. Okay, so that's what's being said over here. It says that adding interval equal to confidence or interval equal to prediction before the final parenthesis will generate a 95% confidence interval for the mean or for a single new prediction. So the prediction interval gives the interval for a single new prediction, whereas the confidence interval gives a prediction for the mean y. Alternatively, to get the confidence interval for the coefficients themselves, which would mean that if I want to know the confidence interval for all the three estimates that I have for the x variables, then I can use the confidence statement and specify what model it's coming from. And this should give me a 95% confidence interval of all the three x variables that are there in my model. Now we'll move on to assumption checking. So we talked about 4 different assumptions. I'll outline them over here. L, I, N, E. So the first assumption, L, stands for linear. The second one is independence. Third one is normality. And the fourth one is equivariance. Now, each of these assumptions can be looked at by looking at either the summary statement or with the help of plots and analyzed if all these 4 assumptions hold good. Because as far as linear regression is concerned, all these 4 assumptions should hold good if it has to be a linear regression model. So linearity can be talked about by looking at the summary statement, by looking at scatter plots of x versus y, and can be talked about by looking at the residual plot as well. Independence cannot be measured by any plot, so all you need to know is that the data came from a random sample. Normality can be looked at using histograms or QQ plot of residuals. Equivariance can be seen by looking at the residual plots. Alright, now that I've outlined what needs to be looked at for each of these assumptions, let's go ahead and check for equivariance and linearity. In our case, the model, now all I want to do is to plot the residuals of the model. So resid statement is what generates the residuals of any model that you're building. And adding a plot statement in front of the resid statement, by doing this, I'm eliminating a step of calculating the residuals and then plotting those residuals. So plot of resid of model house will generate a plot for me that shows me how my residuals are distributed over the rows of data that I have. So the index column that you see over here, it refers to the row number of my data. So since I have over 1,700 data points, I'll have close to 1,700 indices over here. And the residual is, how do you define the residual? Residual is essentially the difference between the predicted value from the model, the predict value of y from the model, minus the actual y value observed, right? So if the model predicts a y value that's greater than the actual y that you've observed, then the residual is positive, and vice versa. So what you see over here is a 0e plus 0, that's the 0 point of the residuals, and anything above that is a positive residual, and anything below that is a negative residual. So ideally what you want is for your linear regression model to have equal residuals above and below 0, which is why you're looking at a residual plot that's sort of random without any pattern associated with it. Now, if you look at this plot, you'll find that there are a lot of outliers, that it's because of the fact that it's a large data set. There are over 1,700 points, and there are bound to be some outliers and some predicted values of houses that give you extraordinarily high values or extraordinarily low values, which makes the residual high. So apart from this, you can observe that there is sort of like a parallel band that's going on above and below that 0 point, which means that the residuals are fairly equally distributed. We do not observe any sort of cone shaped pattern, but all we observe is a parallel band, so to speak. So, by looking at this, you can sort of say that the model um, does account for equal variance, or the E assumption that we're talking about. Now, the same plot can be used to talk about linearity as well. So I can either plot my individual x's against y variable, or I can just look at the plot of these residuals and say. But before that, I'll actually go ahead and plot the scatter plots of. So I need to specify what data is coming from. What have I named it? I've named it as houses, right? So plot of houses, dollar, price, that's my y, against houses, dollar. For example, one of my three x variables was living area. So let me plot that and see what it looks like. You can see that it's roughly linear. It's sort of you can see that the price increases as the living area increases over here, which obviously would be the case, but you need to plot this for all your individual x variables and make sure that you don't see some sort of curved pattern that's going on over here. You can say that this is fairly linear. So I would still recommend that you use these scatter plots for your individual x's against the y variable to check for the linearity assumption. And apart from that, what you can do is you can check the fact that these coefficients that you see on your screen, printed from the summary statement, they all should be significant with a multiple R squared value that's sort of big, in the sense that it's anywhere above 60 percentage, then you can call the linear model as quite good, and the linearity assumption holds good. All right, so that's how you check for the linearity and equal variance assumptions. Now, that's what I've explained over here about the residual plot. It said here that we can see that there are outliers, but the thickness of the plot vertically is roughly equal all the way across. So the homoscedasticity or the equal variance assumption, it holds good. And we don't see any particular trend in the residuals. So there's the other thing where if you see a trend, sort of like an increasing trend or some sort of curvature that's going on, then you can say that the linear assumption does not hold good. But you can see that there is no sort of trend that's going on here in the residual plot. And because of that, you can say that the linearity assumption holds good as well. Now to check for the normality assumption, we can create a histogram and QQ plot of the residuals. So I'll first plot the histogram of the residuals. I would say that given the fact that this data set has 2000 data points, this looks fairly normal to me. It probably has a longer tail on the right as compared to left, but I would still say that the normality assumption is not violated so badly, which the QQ plot can confirm as well. Let me run these two together so that you get the reference line as well. You can see that while you observe a lot of outliers over here and over here, you can observe that most of the points fall on that line, that reference line the 45 degrees reference line that we're talking about. And because of that fact, it can be said that this is coming from a Gaussian data, and the normality assumption holds good. Also, because of the fact that the pattern is denser over here than over here, so it's sort of like withering over here, but a lot of data points are contained on that line, which means that most of those data points are coming from a Gaussian distribution. You just need to identify those outliers and eliminate them, and then run a model with a cleaner data that would give you a better residual plot. But it can be said that roughly this is from a Gaussian distribution, or rather, uh, the normality assumption holds good. So hey, for checking the independence assumption, like I said, we cannot use any plots or histograms to validate that assumption. Um, all you need to know is that the data has been obtained from a random sample. Then we can say that the independence assumption holds good. Now I talk about multicollinearity. So I'll use another data set that's already again been uploaded onto your Canvas page. It's called the autompg.csv. Let me read in that data set. And I want to look at what all variables are there in that data. Let me check that out. So you can see that there is MPG, number of cylinders, displacement, horsepower, weight, acceleration, and whether the car has been a model after 1975 or not. So just by looking at this, there is a simpler way to do all your scatter plots. It's the patch statement. So the patch statement, what it does is it generates all the scatter plots that you need in a single chart. So let me go ahead and type in this patch statement. So you don't have a y variable as of yet, but you have a lot of variables. Whatever variable you want to check your scatter plot for, you can check by just using the plus symbol. So by running this statement, what I'm doing is I'm plotting the scatter plots of all different combinations of these four variables that you see on the screen. So cylinders against displacement would be this one. Cylinders against HP would be this one. Cylinders against weight would be this one. Displacement against HP would be this one. Displacement against weight would be this one. And HP against weight would be this one. You can see that there is nothing funny going on here apart from the fact that there are levels over here because they are discontinuous variables, whereas the plots that you see here are quite linear in nature. So you know that there is nothing too funny going on in terms of linear assumption not being valid. But let me anyway go ahead and build an LM statement, a linear regression model, that predicts MPG from cylinders, displacement, HP, and weight. So I put that LM statement and I name that as model auto. Let me print out the summary of the model auto. Now, what you can see on your screen here is that cylinders and displacement are insignificant variables because their p-values are higher than 0.05 and you don't see any stars associated with those p-values over here, which tells you that these two variables are not significant in the model. Now, for you to analyze why this is happening, we're going to be talking about correlation. So correlation uh, and multicollinearity are related. Correlation is essentially telling someone how two variables, how a pair of variables are going with each other. So do they move together or do they move against each other is what correlation measures. And now let's check for the correlation between cylinders and displacement because they're the sort of variables that aren't significant. When I check for that correlation, I see that the correlation is 0.9508, which means that they go pretty well together, because if you realize the correlation index, it can be only between -1. Um, so it's somewhere between -1 and 1. So zero correlation would mean that there is no correlation. Correlation index of -1 would mean that as one variable increases, the other variable decreases by that same amount. And correlation of 1 would mean that as one variable increases, the other variable increases by that same amount as well. So you can see that they are quite heavily related to each other, and a high correlation indicates that one variable explains the other well, so they move well together. Which means that having both these variables in the model makes it redundant and does not add any explanatory power to explaining why. Now, the VIF function, the VIF it stands for variance inflation factor, which is a test for multicollinearity. And it tells me which variable I need to eliminate because of multicollinearity. So the VIF function comes in a package that's called car. If you haven't already installed that package, you need to use install.packages quotes car and install that package for running the library call statement. But since I already have it installed on my system, I'll run the library car, and I need to see what the variance inflation factor is for each of the individual x variables in my model. And all I need to do is specify VIF and the model name within it. And that gives me the VIF values for all the four x variables in my model. It is a rule of thumb that if VIF less than 10, there is no multicollinearity. Whereas if VIF is greater than 10, it could be a case of near or serious multicollinearity. Uh, Beg your pardon, this is 10, not 20. So you can observe here that the variable cylinder and displacement, they have a VIF value of greater than 10, which means that these two variables are inflating the variance of the model, which means that one of these variables has to be eliminated, and the model checked again to see if the model is significant or if the R squared value has improved. So I'm running a model auto reduced. So I'm first removing that variable that has the highest inflation factor, and which is displacement. And I'm going to be checking a reduced model. All right, so let me go ahead and check why that issue is. Okay, it's a capital C. Okay, let me run this model. Okay, all right, you can still see that this cylinders variable is still insignificant. And while the p-value has come down from 0.3375 to 0.19, you can still see that it's insignificant. And it's also aided with the fact that you can see that the VIF for cylinder is higher than 10. So let me go ahead and remove that variable as well from my model and run an even more reduced model and the summary statement of that. So hey, this LM statement gives me a reduced model, and you can see that the two variables associated with this model are significant. And you can see that the multiple R squared value has gone up from 61% from our original model to 70.64%. So this means that while you cannot directly look at the multiple R squared value and assume that all your variables are significant, or rather, even I can say that you cannot look at the p-value, the overall p-value of the model here is quite less, but that does not necessarily mean that this model is significant. So you need to go and remove those individual variables that are not significant to improve this model, which we have done here. And you can see that the p-value hasn't changed. I actually beg your pardon. The r value, the r squared value was 70.77 in the first case, and it's now 70.64, which would happen because when you are adding more variables to the model, it is natural for the R squared to go up irrespective of whether the variable that you've added is significant or not. So what you need to do is you need to check the adjusted R squared values. It's 7049 for my reduced model, and it's 7046 for my original model, which had two insignificant predictors. So the adjusted R squared actually accounts for the fact whether um, each of your added variables to the model, they are significant or not, whereas the usual R squared value does not account for it. So you can see that the adjusted R squared has gone up for my reduced model, which is indication that my model is a better one. And also the fact that all my variables are not now significant as compared to the previous model. So this is all I wanted to talk to you about today. So today we covered the interpretation of the summary statement of a multiple linear regression. We talked about assumption checking and all the plots associated with assumption checking. And we talked about multicollinearity and the VIF function for multicollinearity. That would be all for this session. Hope you guys enjoyed it.